To be here. I hope you've been enjoying the work, the summer school so far.
One
Yeah.
more thing, you got an email inviting you to the New Year starting tonight, except that it says in the Israel Museum, which is wrong. Okay? It's in the Science Museum. They're all next to each other, but it's not the right museum. Okay? So it's the Science Museum. Okay? Not the Israel Museum. Science Museum.
Okay. That's the most important thing you'll hear at the for this talk. Where to go for the party. But otherwise, I'll tell you about Type 1a supernova. I know at these schools there's just a fire hose of information coming at you. It's sort of more material than any brain, I think, can handle in 1 week. And this talk is going to contribute to that, I have to admit, because I was asked to talk about Type 1a supernova, which is an important topic, but it's a broad topic. You could do, of course, a whole conference on 1A models, and I think this will be one of the few talks to actually cover it. So what I'll try to do for this talk is just kind of give you a broad and admittedly somewhat shallow overview of the landscape of Type 1A supernova and their models and observations. And then in the next couple talks that I do in the next couple of days, I'll sort of dive more deep into some of the physics and practical calculations you can do trying to understand spectra and light curves and radiation transport. But this is just kind of a broad brush overview of what's going on with Type 1a supernova. How many people here, I'm curious, are working on Type 1a supernova or interested in Type 1a supernova? Okay, so there's a few. Yeah, it's an important subject. I'll say. I mean, I guess personal history. That was the topic I started getting into when I was in graduate school. I was back in like 2000 or so. It was a very hot topic then because this was a few years after they had used supernova to measure the expansion of the universe and the acceleration of the universe. And so, of course, every observer wanted to go out and find more Type 1a supernova and quantify their differences and improve the standardization. And every theorist wanted to claim they were going to explain what the supernova were and how to control the systematics and so on and so forth. And so now we're many, many years after that, and I think we actually still don't know what Type 1a supernova are exactly. In fact, in some ways, the situation's gotten more opaque, because back then there was sort of a favored Chandrasekhar mass model, and now it's more wide open of what's going on with these supernova. And so as the observers kind of had classified these and characterized them in great detail, of course, they went on and got interested in lots of other sort of weird and more exotic supernova. There's only so many Type 1a supernova spectra you can look at without getting bored, and then the theorists tend to follow the observers into sort of new fields. But we still have very fundamental questions about what Type 1a supernova are, and I'll give you a broad overview of that, and I think it's a ripe field for work. There has been a lot of insight on the theoretical side of what's going on, even if we haven't come to sort of one converged picture of what's happening. So what I'll do kind of for this talk, and again, like I say, it'll be sort of a fire hose of information, but I'll give you a very brief overview of what we see from Type 1a supernova, what's going on there. I think you'll have more talks about the detailed observations in general of supernova, and then I'll go through sort of the zoo of different models that we have for explaining these. I think the word zoo seems to come up a lot in this winter school, so that may be some indication of the confusion we have, but there's many different types of models. Back in the day when I started working on this, people were largely convinced that the right model for Type 1a supernova were explosions of near Chandrasekhar mass white dwarfs, carbon-oxygen white dwarfs. Over the time, the stock has fallen in that model for several reasons that I'll talk about. And other models, such as sub-Chandrasekhar explosions, which back at that time were considered ruled out, have come back to life as very interesting and in some people's minds favored models for explaining most of the Type 1a supernova. And as well, white dwarf mergers or other sort of double white dwarf systems, which again back in those days was considered unlikely to produce a Type 1a supernova, have turned out to be a very rich field and potentially important progenitors. Now, if you ask people nowadays, many people would say, well, probably maybe all these things are going on and all contribute in some rate to the Type 1a supernova we observe. Some would say that. And our work is to sort of figure out, which type 1a supernova maps to which model. But within each of these kind of general classes, there's several different sort of variations on a theme, which I'll try to give you the scope of, and you can, of course, then look into more detail of everything that's going on. So let me give you some general sort of observational background to sort of guide the rest of the discussion. What do we know about type 1a supernova? Usually it's the simplest things that are sort of the most robust and where we learn the most. The first thing is that we see type 1a supernova. This is maybe the most famous picture of a type 1a supernova, any supernova, supernova 1994D. But we see type 1a supernova both in spiral galaxies or near spiral galaxies and elliptical galaxies. And so we see them not only where there may be star formation, but in old populations where there's no star formation or regions of galaxies where you don't see any star formation. So that's sort of the fundamental idea that these are not coming from a massive star population, and why we think about older systems like white dwarf systems as the explosion mechanism. And you can do a very simple calculation. In fact, I think I was asked this on my qual exam, and I don't know if I got it right, but you can just ask the same basic question of, if you take a carbon oxygen white dwarf, round Chandrasekhar mass or solar mass, and you blow it up, how much energy, if you burn all that carbon and oxygen, how much energy do you get out, right? And so that's a good question. How much energy do you get out? How would you estimate that? Well, you'd say something like the mass, which is something near solar mass or so, over the mass of carbon would be the total number of atoms you have, and how much energy do you get out from burning a carbon, roughly? MEV scale, something, a few MeV or something. So then if you know these numbers on your qual exam, you can estimate how much energy you get out. It's something a few times, a couple times 10 to the 51 ergs. All right. And then you can ask, well, what's the binding energy of a carbon oxygen white dwarf, right? What's the gravitational binding energy? Something like gm squared over r, with some number out here. Depends on the structure and the internal energy. But you plug in numbers here, and you'd find something like 5 times 10 to the 50 or something. So if you can, it's a close call actually. But if you can burn most of the star, most of the carbon and oxygen in a white dwarf, you'll get enough energy to unbind the star completely and give yourself a healthy velocity for the kinetic energy. But you do have to bind a good fraction. You do have to burn a good fraction of the carbon oxygen white dwarf to unbind it. But that was the idea, and this goes back to I think the 50s with Fowler and Hoyle. Suggested, well, if we could somehow ignite a carbon oxygen white dwarf, we can make a supernova. And if that's the level you care about type 1a supernova, maybe you think the problem is done, at this level, right? We blow up a carbon oxygen white dwarf, we can explain the supernova. Well, you want to go one more level, because we'd want to explain the light curves that we see. And Udi's going to give you some background about modeling light curves in a second. But the basic idea is, if you blow up a white dwarf, even though you give it a lot of energy, a few times 10 to the 51 ergs, it's all in a very compact system that's very optically thick. So it's not going to be able to radiate until it's expanded by some large factor, and that material has become translucent. So it's going to have to expand from white dwarf radii out to something about the size of the solar system. And in that process, all this energy that you dumped in from burning is going to be lost to expansion, PDV work, and all go into kinetic energy. So you really wouldn't see anything from this explosion of a white dwarf if it weren't for the fact that when you burn carbon and oxygen under these conditions, you can go to NSE, nuclear statistical equilibrium, and produce, in general, iron group elements. And the favorite iron group element to produce when you have equal numbers of protons and neutrons, which you do in a typical carbon oxygen white dwarf, is nickel 56, 28 protons, 28 neutrons. And that happens to be radioactive, and it'll decay on some time scale relevant to the light curve of the supernova, producing what we see. So I always found this kind of a fascinating quirk, that if it hadn't been the case that these explosions produced radioactive nickel that had about the right decay time scale, you'd have this powerful explosion that really wouldn't be visible at all. You wouldn't really see anything until maybe it started interacting with the interstellar medium. But the fact that you make a good amount of nickel powers the light curve, so nickel decays to cobalt through electron capture, and basically it decays to some excited state of cobalt, which then decays through some gamma ray emission. And similarly, cobalt goes to iron, producing some gamma ray emission and also some positron emission as well. So here is just showing you the radioactive decay energy. At early times, all of that decay energy is trapped. All those gamma rays are trapped and they heat the ejecta. At later times, the gamma rays start to escape, and only a fraction is trapped and heats the ejecta, right? And then the light curve we see is basically just that radioactive glow following the explosion, the radioactive glow of the debris. Okay? So we know that this is basically the right picture. There's actually direct evidence for it, where at least in one case we've actually seen the radioactive decay of cobalt from a nearby type 1a supernova, 2014J. So if you actually look at cobalt decay, well, most of the energy comes out in these transitions from the excited state of cobalt. The most prominent line is here at 847 keV. And in these gamma ray observations with integral, you can see that they detected a strong gamma ray emission at 847 keV from the escaping gamma rays. The second strongest line out here at about 1.2 MeV was detected as well. So we've seen, directly that, radioactive decay of cobalt is powering these events. Okay. And the light curves themselves, well, there's some range in their brightness, I'm sure, as you know well, maybe a factor of 3 or so in brightness among the more normal events. And then there's this famous relationship that the brighter events tend to have more slowly declining light curves, which is used for the standardization. This is presumably reflecting some range in the nickel production in the explosion, some factor of several in how much nickel you make. And this is also, I think, a plot that goes back many decades, but showing as you, if you try to calibrate these and correct for their luminosity and durations, you can sort of put them on a single curve, which is what's been used to standardize these for cosmology. The story of this is a little bit more complicated because the relationship you're seeing here is really only in the optical B bands, or maybe the V band. If you look at the light curves in different bands, so the B band kind of goes up and down nicely, and the V band a little bit more slowly. But in the R and the I and the infrared bands, you start to see this double peaked behavior, the secondary peak, which we can talk about if we're interested. But essentially, this width luminosity relationship only holds in certain bands. It's not an overall bolometric effect or an effect that happens in every band. And so if you look at this type 1a width luminosity relationship, which for many years was sort of the gold standard thing to try to explain, this is sort of what the data look like, at least some sample of it. So here's the brightness. Here's some measure of how fast they decline, how many magnitudes they drop 15 days after peak in the B band. And you can see there is a trend here. It is rather noisy. There's a lot of scatter here. And so this is the range of normal events that change about a magnitude or more in their brightness. So these would be nickel masses in the range of 0.3 to 0.7. And then down here we have these subluminous events, sometimes called 91BG likes, because 91BG was the kind of first great example of those. And up here some extremely bright events, which are some called super Chandra events. So one thing that's asked about this is I mentioned before that some people think that there's many different channels of producing type 1a supernova. And you can ask, well, if there are many different ways of producing type 1a supernova, how come they all tend to lie on this nice Phillips relationship? And so I'll leave it up to you to whether you think that that's plausible, whether there could be many channels or different channels contributing to different pieces of this and still be consistent with this relationship. Maybe you might think that, well, these tend to kind of fall off a little bit or at least steepen from the relationship, so maybe these could low luminosity events could come from a different source, or maybe these very high luminosity events, which also tend to fall off, could be a different channel. But in principle, I don't think it's impossible that there's more than one channel contributing within this main population of normal 1As. And in fact, there is some evidence to that, at least that there's some diversity. Here we go. Sorry, I don't know what I'm doing. Where if you look at, now this is kind of just zooming in on the brightness width relationship for the events in sort of that more normal range. And of course, as astronomers do, they've kind of flipped the axes here, so brightness is now going this way and width is this way. But you can see that there's a relationship here, but if you break it down actually by their populations, their host populations, so red here are high mass host galaxies, so presumably, on average, older stellar populations, and the blue are lower mass populations. You can see that there's some trend here that the dimmer events tend to happen in the higher mass, older stellar populations. Okay, and so you could argue that maybe this is a sign that there's more than one channel of producing these type 1a supernova, or maybe you might argue that there is just one channel, but there's some sensitivity in that channel to the age of the galaxy and somehow. But there at least are indications of this sort that suggest there's something about the host system and hence something about the progenitors that come out in the observables that we see. And these kind of effects have to be accounted for and corrected for if you're doing cosmology with type 1a supernova. And just a bit on the spectra. Now, my next talk, I'll kind of explain spectra in more detail and tell you how you can interpret them and how you can actually calculate them yourselves. But essentially, the spectra of type 1a and really all supernova tend to look kind of quasi-thermal with quasi-black body with these broad absorption features. And for normal 1As, it's at their peak brightness, you're seeing mostly intermediate mass elements like silicon, sulfur, and calcium. And within those normal events, in most type 1a you see, there's sort of remarkable similarity in their spectra from event to event. But there are peculiar events, or at least ones where the spectra look different. If you go to that low luminosity event, you see stronger features here and this broad absorption due to titanium, which is an element that comes in once you're at colder temperatures. And if you go here, this is an overluminous event. You see weaker absorption from silicon and other intermediate mass elements. All right. So again, you could ask whether these are part of the same family or whether they come from different progenitors, or whether they're just sort of extreme examples of the normal events. And I think those are still open questions to ask.
So is that pretty systematic, that more lines in the less luminous events and fewer lines in the brighter ones?
Yeah, I mean, it tends to be the case that, well, there's these class of 91Ts which tend to be brighter than average, and they tend to have these weaker IME features. But there are examples of these even brighter events, the so-called super Chandrasekhar events, which lie, up here, and they're called super Chandra because if you naively, estimate the nickel mass based on the brightness, it's up towards 1.2 solar masses. And you also see, in these cases, strong absorption from silicate and sulfur, actually stronger than you see in that 91T. So they look kind of normal. So not all bright events lack those features. Yeah?
I'm just wondering why the sort of lower luminosity super Chandrasekhar 1 is included. Or, like, there's something else that...
Lower luminosity super Chandrasekhar. So this event here.
Yeah, that does.
Yeah. So again, there's super Chandrasekhar, which should be said in quotes. So in these events, if you just look at the nickel mass, and then you say, well, there's also some silicon and sulfur and other mass there, then you start to get above the Chandrasekhar mass. This event here was not all that bright, but actually spectroscopically and in other ways it resembled these events. And so people have argued that there might be a lot of dust extinction and actually should have been brighter. But that's sort of not a really well-defined class in all ways. Okay, this plot for some reason hesitates to go forward. Here we go. So these were the spectra near peak brightness. You see a lot of intermediate mass elements. As time goes on, you see more and more iron group elements. So this is now looking at late times, what we call the Nebular Phase. And again, I'll explain more about spectra and how to make sense of all this in my other talk. But if you look at, let's say, 200 days after peak, you start seeing mostly emission from iron group elements. So these are from forbidden iron lines, okay, indicating that the core of the supernova ejecta is mostly iron group elements. Okay? It's in contrast to other sort of supernova like type 1Cs where you see more oxygen and other elements. So the basic picture we've had is that whatever exploded produced some sort of stratified compositional structure, okay, where the inner regions were mostly iron group elements, and then you had outer layers of silicon, sulfur, other intermediate mass elements, maybe outer layers of just where carbon burned to oxygen, and then maybe there's even some unburned carbon and oxygen. Okay? So this is a very famous W7 model that was published by Nomoto in the early 1980s, which you may have heard of, and everybody used it for many years, and a lot of people still continue to use it, basically because it has the right compositional structure roughly to explain what we observed. But it's actually kind of a faked up model. So what Ken Nomoto did here is he knew from those observations that I just showed you, the spectra and light curves, that you had to make some amount of nickel to make the brightness, and you had to have sort of a layer of silicon on top of the nickel to match the spectra. So he took a Chandrasekhar white dwarf and he sort of put in a burning front, and he tuned the speed of that burning front so that it burned at just the right speed, that in the higher density regions you made nickel, and then you started to get partial burning in the lower density outer regions. And he made something that worked, but it didn't fully explain the physics of what was going on. In the interior here in this model, you see other iron group elements, in particular nickel-58 and iron-54. That's because burning here is happening at the center at very high densities where you can actually have electron capture. So you can have electrons capturing onto nuclei and turning protons into neutrons. And so you no longer have equal numbers of protons and neutrons, which gives you nickel-56, and you produce these neutronized elements of nickel-58 and iron-54. Okay.
What part of the observations indicate that this is the structure of the abundance of elements? How did he know that? Like he knew that about the amount, but how did he know that the nickel is in the center and the other elements are outside? What part of the observations?
Yeah, I should have shown a better series. But if you look at, this is at peak or sort of early times, you see all elements of mostly intermediate mass elements, silicon, sulfur, and so on. And then as time goes on, these get weaker and the features from iron become stronger, and at late times you see all iron group elements. So if you had a composition that was fully mixed or iron was everywhere, at this early times or near peak, you would see mostly iron group elements. So I should have shown a plot showing this, but I'll talk more about it in my other talk. As time goes on, we see deeper and deeper into the supernova ejecta as it thins out and the photosphere recedes. And so you can sort of do a tomography of the ejecta. At early times, the photosphere will be out here, and you'll be seeing mostly silicon and sulfur. As time goes on, the photosphere drops, and you'll see mostly iron group elements. And so there's strong evidence just from the observations that you get the stratified composition, and that's some constraint that any model has to address. Any other questions? Yeah.
So then what the density necessary to burn something into the nickel in this case? The density criteria. Is there any, do you need to burn something at high density to produce nickel?
Yeah, you have to have a high density. You have to reach temperatures sort of in excess of 5 times 10 to the 9 Kelvin for reaching burning to nickel. And then you need to be above a certain critical density. And so I'll say a little bit more about that as I go on. Yeah. So the last thing I can say is what's the geometry of the ejecta that's producing these explosions. That would be the best way to try to understand what we're seeing is if we could actually look at it. Of course, the supernova we see are too far away to resolve. We just see points of light. We can look at supernova remnants in our own galaxy that we can resolve quite well. Here's Tycho. And you can look at that and say, well, it's pretty spherical. That's true. But, it's complicated. This has been interacting with the interstellar medium for some hundreds of years. And it's hard to know whether we're seeing the ejecta itself or properties of the interstellar medium shaping the ejecta as well. The other sort of observational handle we have on the geometry is to look at polarization measurements of supernova. And polarization provides us some handle, even at early times near the peak of the light curve, of what the geometry is, even when we can't resolve it. And that's because as light scatters around in the supernova ejecta, electron scattering is the dominant opacity, and electron scattering is a polarizing event. So it polarizes the light with this sort of pattern, just like the sky above us is polarized by reflecting the sun's light. Of course, if you could resolve this and look at any point on this disk, you would see polarization. But if you can't resolve it, which you can't, you integrate over this. If it's perfectly spherical, you'll get zero polarization. But if the ejecta has some net asymmetry to it, then when you integrate it over here, there'll be some preferred direction, and you'll have some net polarization along some axis. And so you infer some asymmetry of the ejecta, or if there's some sort of clumpiness of the ejecta as well. So this is sort of our main handle on something about the geometry of the ejecta. And there have been a lot of observations of spectropolarimetry of supernova and type 1a in particular. It's not an easy task to do observationally and also to interpret what you see. But here's one old example of a kind of normal type 1a supernova. The spectrum looked normal with these usual features. But you can also look at the polarization here, which is low in these regions. And that's because lines tend to depolarize the light. So you don't see much polarization here. But this region here, where there's not many lines, you have mostly electron scattering. You see sort of a net polarization here. Okay? And that reaches maybe about 0.4%. So it's not very highly polarized at all. And that indicates an asymmetry. If you try to compare it to models of this polarization, that's pretty modest. Pretty close to spherical, maybe 10% distortion. Depending on how you model it. If you modeled it this kind of ellipse, it would be sort of axis ratio of 10% larger in one way. Yeah?
Because the lines start from recombination. What did you say?
So, yeah, so the lines, basically interaction with the line would tend to depolarize the light, either because the line will absorb and thermalize the light and put it on some other wavelength, or because just because of effects in the line transport. So, you excite some transition and you get sort of collisionally distributed over all sort of degenerate sublevels of that. And so you decrease. So generally, lines tend to be depolarizing. Of course, some lines are not depolarizing. In this particular event, there was an absorption of calcium that actually had a polarization peak, and sometimes you see that as well. But what's probably going on there is you have maybe a clump of kind of calcium or something that's blocking the photosphere and creating some enhanced polarization over this region. So by looking at polarization over individual line features, we can say something about the distribution of different elements that, in this case, would suggest maybe we have a clumpy distribution of calcium. But the global asymmetry is moderate. Okay, but it's very hard to interpret these polarization observations because it's sort of a poorly defined inverse problem. There's a lot of different geometries that may be able to produce the same polarization spectra, so it's hard to really have a perfect inference of what's going on. But you can say something about whether it's asymmetric or not. Okay. Okay, so that's sort of that was sort of a brief, very brief sort of summary of some of the key observational properties of these supernova. And then I'll now kind of use that as a jumping off point to talk to you about different explosion models and how they may or may not agree with those observations. Any other questions on that before I move on? Yeah.
Is it so? Some of these the 91T spectrum that you showed is it difficult to differentiate a 1C from a 91T? I guess these silicon lines are really distinctive in one is.
Yeah. It can be hard. I mean, there are 1Cs that resemble type 1As in some way. They have basically spectroscopically similar properties. The you know, the 91Ts are actually quite bright. They're even brighter than normal 1As, whereas type 1Cs are usually quite a bit dimmer than 1As. And so the assumption is that the 91Ts are 1As that produced a lot of nickel. And it's hard in a core collapse supernova to produce that much nickel. But I think there's a lot of questions that could be raised about, you know, which events really belong to the class of type 1As and which don't. Okay, let me tell you a bit about the different explosion models. There's sort of three general classes, although it depends on how you break this down. I mean, often you'll hear it kind of broken down into a binary thing. You have single degenerate models, and you have double degenerate models for the progenitors of type 1As. We're pretty sure what's going on is there's a carbon-oxygen white dwarf that's exploding, but how you actually trigger that, well, it's not going to explode on itself. It needs a companion star, and that can either be a degenerate star, so another white dwarf, or a non-degenerate star, a main sequence star, maybe a red giant, maybe a helium star. But you know, this is kind of a coarse breakdown. Within each of these classes, there's several different kind of stories of how you might explode things, and some of them are more or less similar. So I'll talk first about sort of when you have stars near the Chandrasekhar mass that might explode as a deflagration or a delayed detonation. There's, you know, explosions that happen sub-Chandra that could be in either a single degenerate or double degenerate. And then there's mergers, which may be super Chandrasekhar or maybe not. Okay? So I'll give you a little bit of the flavor of each of these. But again, I'll have to go through fairly quickly. So I'll start with the classical Chandrasekhar mass model. I say classical because for a long time everyone said, well, this has to be the right explanation. We have a white dwarf. So I'll just show this, you know, old picture of the accreting white dwarf from some non-degenerate companion star. This could be a main sequence star. It could be a red giant. Fortunately, because Lars went before me and Sturl went earlier today talking about binary evolution and accretion onto white dwarfs, I don't have to go into any details of how this process happens. I can just say, well, somehow this white dwarf, which started at some low mass, grows by accretion towards the Chandrasekhar mass, burning stably, so it's growing in carbon and oxygen. But you should keep in mind that that's not a trivial process, as Lars showed. There's a very sort of, you know, narrow region of accretion rates where the, you know, accreted material can burn stably on the surface to carbon and oxygen. And actually getting this up towards the Chandrasekhar limit is tough. We're not sure that it can happen or that it happens at the rate we need. But in any case, for this purpose, I'll just assume that we can get there. And so what happens when you bring a white dwarf up towards the Chandrasekhar mass? Well, something has to happen. And what happens is that as you approach that mass, but you don't actually quite get there, temperatures in the center become hot enough that you start igniting carbon burning, okay? And initially you start burning the carbon, but it's not a runaway, it's not an explosion. The carbon can burn, the energy can be carried away initially by neutrinos that cool it off. When that can't happen, then the hot regions become convective. You have some hot stuff at the center burning. This surface here is kind of showing you a burning isosurface. And so the hot material kind of convects and boils over. And so you have this phase that's called, you know, people argue over what to call it. Sometimes it's called simmering, sometimes it's smoldering. But basically a period of some 100 years, 1,000 years, you know, hundreds of years at least, where you have burning in the center and you just sort of have a boiling white dwarf. It's kind of amazing. You have this incredibly dense material, but it's boiling, right? And so here, this is a simulation of that phase of pre-explosion simmering. This is not the whole phase. This is sort of the moments right before the thing is going to explode. And you're seeing burning here, and this is showing you sort of the flows, the convective flows that are set up by the burning in the center. The color coding here, I think, is by the velocity, so there's some outflow velocity. And it's kind of hard to see, but it actually sort of has some circularization that kind of goes back around. And so this convection is kind of strange. It looks like it sort of has a direction that it's pointing to. And that is just a kind of spontaneously broken symmetry, that this convection tends to pick out a special direction and have sort of a dipolar character to it. But you can see that direction tends to kind of wander around as time goes on. But basically, you have convective flows coming up and down in this burning. This convective region grows throughout the star. It can grow to almost the solar mass or so. So most of the star becoming convective. Temperatures are raising, so burning is becoming more and more effective. Oh, here he slows it down. That's nice. So this is work by Mike Zingali. And so the idea is that eventually, as you start, temperature keeps going up. Burning rates are very sensitive to temperature. One of these points is going to become a hot spot that can run away, that can burn faster than the convection can cool it, right? So here, hot spots are rising and cooling. But at some point, one of these hot spots is going to go off. And these types of simulations of that convective flow are trying to understand where ignition happens. And it's hard to say, but you do see some hot spots going off. And what it looks like is the ignition is unlikely to happen right at the center. It probably happens in some blob just slightly away from the center. Or if it happens at the center, it probably flows away from the center quite quickly. And it may be at a point, or maybe there'll be several points that sort of ignite around the same time. And what's that?
Will it drive a symmetry if you?
Yeah, so I'll say that. So yeah, if you'll get quite a different result if I ignite, say, one, plume here. I'll get quite a different explosion than if I ignite sort of many plumes in a more spherical configuration. And so, again, this is still work people are working on, but it looks like maybe the off-center ignition is more likely.
What's the length scale?
What's that?
Length scale.
I think this is showing this is showing the inner 1,000 kilometers or something.
Yeah,
The objective.
Only the inner.
So it's just the inner regions, yeah. So ignition is not going to happen way far from the center, but it might happen just slightly off center. So what happens when you light an ignition? So you may know that. So when you start having some runaway burning in the white dwarf, there's two different modes that it can take. It can take a deflagration, which is basically a subsonic flame. So you get some very thin flame. The thickness is set by sort of the burning length behind the flame. It's mediated by electron conduction, so electrons that are hot behind the burned material sort of propagate forward and burn stuff in front of it. Or you can have a detonation, which is basically a shock wave running through that's compressing material and burning it behind it. And that energy that's released by burning behind that shock wave actually can sustain the shock wave as it goes, at least until it propagates into low density material. Okay, so there's these two modes which look quite different, and so that means that there's different ways of blowing up the white dwarf that have been explored. The first ever looked at back the 70s or so by Dave Arnett was just suggesting that you detonate the white dwarf, which is a rather simple process. You just run a shock through it. But that was, early times was ruled out because basically one of the key differences between the deflagration and detonation is if you have a subsonic deflagration, well, the deflagration can send out pressure waves ahead of it. And so the material ahead of the deflagration front knows that there's something coming and can sort of expand in response to that. Whereas if you have a supersonic detonation, well, stuff ahead of the detonation doesn't know it's coming. There's no way to communicate that information. So it remains at its same density. And so if you take a Chandrasekhar mass white dwarf and run a detonation through it, well, it's all at pretty high densities, and you burn basically the entire white dwarf to nickel-56, okay, which is not such a bad model, but it is ruled out for the reasons that I talked about before, that when you look at the spectra of type 1a supernova, they show strong lines of silicon, sulfur, and other intermediate mass elements. If you burn everything to nickel-56, you should just see iron all the time, which is, or iron group elements all the time, which is not what we see. So the simple model was ruled out. You might instead talk about a pure deflagration, so you ignite a flame, and then that propagates out subsonically. But this sort of has the opposite problem, is you have a weak explosion. So now as the flame moves out, the star can expand in response to that. And so you have sort of a race between the flame trying to move out and burn the star and the star trying to expand its way out is in response to that. And I'll show you in a second that when you run these deflagration models, you tend to get fairly weak explosions that give you low velocities and other features that are not reminiscent of normal type 1a supernova. Okay? So kind of the happy medium. So I don't know if this is just right is if you kind of invoke both of these. So you start out with a deflagration, the subsonic burning, the star white dwarf starts to expand a little bit in response, and then at some point you switch to a detonation once you've lowered the densities enough, and then you can produce the right composition. I'll show you an example of that in a bit. Okay? Yeah. So let me show you a movie here of what deflagration looks like. So a deflagration itself, if you just had sort of a simple flame, it would be rather easy to calculate the laminar speed of that flame as it moved out. But the actual dynamics in 3D are much more complicated because as you burn, you produce hot material below the flame, which expands to go into pressure equilibrium, and then it's low density, so it's buoyant, and it tends to rise up. And it's subject to all these Rayleigh-Taylor instabilities and other Kelvin-Helmholtz instabilities and so on that corrugate the surface and produce a more complicated burning pattern. So this was work that a lot of people were really focused on for a long time, trying to model this complicated burning in 3D. So here's one example. This is the initial condition they put on here for the ignition. Whether that's the right one we can debate. It's rather centrally ignited with lots of different sort of corrugation there. And so you can see here as it burns, there's a lot of hydrodynamical instabilities that set in here in turbulence, which sort of corrugate the flame front and increase its area. And this is all buoyant and it's sort of rising up like a lava lamp. Okay? So the actual speed at which this deflagration burns is set a lot by the buoyancy-driven effects and the turbulence associated with that, which sort of set the flame front. Right here, you have a lot more surface area for burning. So you get this, quite complicated burning geometry here. But one thing you notice is that it's somewhat ineffective at burning the whole star. There's kind of holes in between here. I don't know why it's showing you helium production. You can show it again. So there's holes in between the flame front where unburned material was left behind. And as you can see, as the flame is burning, right, and you have this high pressure region, it's sending out sound waves that expand the star. So the star is expanding and trying to outrun the flame front itself. You can see that here is you can see the star basically expanding alongside. So densities are dropping. A model like this, you do burn enough material to unbind the star, but it's a rather weak explosion. Maybe less than 10 to the 51 ergs. And so, again, the way to fix that up is to say, well, let's start out with a deflagration and then transition to a detonation at some phase to turn that sort of weak explosion into a healthy one. And so, this was explored, back in the 90s by Kokolov and Livnay and others. Here's just one example. This is 2D simulation showing, this is just two different models that were ignited slightly differently. So here, lots of different hotspots were put in the center. Here, less hotspots were put in the center. And you start out with a deflagration, so these flames, these highly irregular flames start burning outwards. And you can see these buoyant bubbles tending to rise. The star is expanding, the densities are dropping. And then at some point, we invoke a transition to detonation somewhere, maybe at one point, maybe at several points. Now, how does the deflagration transition, the subsonic burning transition to a detonation, the supersonic burning? That's one of the key questions that sort of remain. I mean, I think Lars always says you can always invoke one tooth fairy per paper. You're always allowed one sort of trick. And so this has been the trick for many years of saying, well, we're not quite sure how this transition happens. It's happening on scales that are small compared to what we're resolving in the simulation. But let's see what happens if we say at some point that the deflagration turns into a detonation. And if you put that in by hand, then you start to get this shock wave that propagates back in quite strongly and starts burning away all that unburned material that was left in the center, as well as burning material on the outside as well. And so you wind up with something that looks like that simple W7 model I showed you, that 1D model, where mostly nickel in the center, mostly intermediate mass elements on the outside. It's kind of color coding the atomic weight. And here, there's some irregularity and clumpiness in the center from the deflagration, but roughly it looks fairly spherical. Okay? Questions on that? These are the same mass. So these are both Chandrasekhar mass, and the only difference here, as you saw at the beginning, was how many ignition points we put in. So here there was a lot of ignition points, and so we get a very strong deflagration. Here there were just a few. We had a weak deflagration. And so this star expanded more in the deflagration phase, right? And so so when it detonates, the densities are lower here than they are here. And so when the detonation goes off and starts propagating through, well, here the densities are higher, so it makes more nickel, and here they're lower. No, they both transition to a detonation. So weak ignition, a little maybe counterintuitively, the weak ignition leads to a more nickel mass, because you have a weak ignition, you have a weak deflagration, so you have very little pre-expansion of the star before you turn on the detonation. So densities are higher.
But that depends on when did you choose to turn on the
Yeah, right. So one thing that's...
we could think that if it was weak, it would turn on later.
Yeah, exactly. So you sort of have...
comparisons when you turned it on at the same time.
Yeah, so there's some condition here for when to turn it on, which is when, the flame front reaches some density and when there's a certain amount of turbulence here. So there's sort of the same criteria of when this flame front reaches a certain density, essentially, to turn it on. But you're right, there's sort of two free parameters here that we're playing with. One is how do we ignite the star in the first place, which sets out how strong the deflagration is. And the second is when do we turn on this detonation. And depending on when you do that, you'll get more or less nickel mass. The idea is, the earlier you turn on a detonation, the more nickel you'll get out. So it's kind of nice in the sense that you can make a range within, the same mass star. You can make a range of different nickel masses, a range of brightnesses of your type 1a supernova, just due to these kind of stochastic effects of how strong the ignition was or when the detonation happens. But it's a little unsatisfying in the sense that the physics that was crucial here of going from a deflagration to detonation was ignored in a sense. It was just put in by hand. Yeah?
Would you expect the strong ones to be more symmetrical than the weak ones?
Yeah, in general, you kind of see that in these kind of simulations, right? So here you see, the deflagration, you had more deflagration going on here, so you have more of this sort of turbulent structure in the center. Whereas here it was, the detonation smoothed things out.
You would expect like the brightest events to be more asymmetrical than the
Yeah, there might be. So that's an interesting point. Yeah, you might be interested to look at, say, how polarization, which measures asymmetry, might be related with the luminosity. That may be something to look at. The outer layers of these are still pretty spherical, right, in both cases. So in early times when you're looking at mostly the outer layers, it may be hard to tell. But yeah, there's some diagnostic there that could be explored. So I said this deflagration to detonation is sort of a tooth fairy. I mean, people have done a lot of work on it, and it's an important problem. It's a hard problem, and it's not completely arbitrary. There's some physics to suggest that there would be a deflagration to detonation. In fact, there are deflagrations to detonations that happen on Earth. In your car, for example, if your engine is pinging, that's a deflagration to detonation transition. The flame, the flame that should be burning in your engine cylinder, which should be a nice deflagration, is spontaneously detonating and giving you an inefficient burn. So you should add more octane to your fuel. So people have studied that a lot on terrestrial experiments. But what's different in your car engine is that it's sort of a confined cylinder, and you can have waves, pressure waves bouncing around and converging at some point to make a deflagration turn into a detonation. In a white dwarf, there's sort of no walls or anything to sort of confine things and have pressure waves bounce around and form a position of high density and temperature to detonate. But there are physical effects that may lead to detonation. This was explored here in some papers. This is just showing you, a zoom into a tiny piece of the flame front where you can actually resolve some of the turbulence, but simulated at different densities. And the main point is if you're at high densities, this flame front is very thin. That is the layer where you're doing burning, since the densities are so high, is very thin, millimeters or so. But as the flame moves out into lower densities, well, that flame thickens. So the region where the burning happens is happening over a longer length scale. And eventually it gets into a regime where the length scale of that burning is somewhat comparable to the turbulent length scale. And so you have this regime here where the burning is sort of being mixed up. The fuel and the ash is being mixed up. It's called the sort of distributed burning regime. And it's thought that somehow in this regime is where you might be most likely to get this transition, because you might mix up pockets of fuel with the flame and maybe make a pocket of fuel that you can burn all at once and turn into a detonation. Okay? And there's other papers exploring sort of the physics of how this might happen. It's still an uncertain thing because it's a stochastic process. So you can run a simulation like this and see, okay, I'm getting sort of pockets of fuel mixed up in this hot ash. But even if you don't see a detonation happening here, it doesn't mean that it never happens, right? This is just one little piece of flame. It's a stochastic process. It just has to happen somewhere in this large deflagration front, right? So even if it's a very rare kind of event, it may still happen somewhere on that large deflagration front. And that's one of the issues. Yeah?
So if this running happens at lower density.
Yeah.
But in the previous slide, the argument was that the lower density, due to the deflagration, led to a weaker, led to less burning. So is there any tension there, or am I?
Yeah. Well, so here, this in these simulations, it use kind of that idea of this transition. So it says, you have this flame going out, and of course density is dropping with radius. You can't really see that here, but densities are lower out here. So the flame is going out. The star is expanding, so the densities are also dropping globally. But at some point, the flame will reach a point where the densities are low enough that you will enter this regime and you think you might detonate. And so you're right that you'll have to take into account both the fact that you're propagating out into low densities and this sort of overall expansion. And in these simulations, it used that criteria. Those are both taken into account because it used a density criteria. It said when was the flame sort of in this density regime where we expect there to be a lot of turbulence and so on. But you're right, and it's also a stochastic process. So maybe there's not a particular density where it always detonates. Maybe sometimes it detonates earlier, sometimes it detonates later. We don't know that. We can't resolve the physics of that, on the scale that you're doing the full star simulation. So I think it's still a question of what's going on. In any case, you can do these simulations and invoke a detonation and get some structure like this, and do model light curves and spectra. And you can see that this is a time series of spectra. Red here is observations. Black is model. The model does pretty well, sort of on an overall scale at matching these features, at different times. So it's fairly successful in fitting the observations. So that's a benefit. Yeah.
About that double detonation model. So aside from the fact that we're kind of we have an embarrassment of how does it work.
Right.
Do you have any idea how one can you're saying it's successful. There's no observation hint that it's not working. So is there any idea one can attack such a model, or
Yeah.
just accept it because the light curves are great?
I'll get to that. Yeah, so there's several objections to the model. So on the side of kind of fitting supernova light curves and spectra, it does pretty well, provided that there's this miracle that happens. But there's other constraints that tend to disfavor it. So this is why this was popular for a long time, but there's other observations now that cause problems for it, which I'll get to. That's a good question. Let me give you a twist on this now. I mean, that was a model that was roughly centrally ignited, or at least there were several points that were ignited. But I said before when I showed you that sort of pre-explosion ignition, simmering phase, that you're actually very likely that you might ignite off-center. And then the situation might look very different, even if you're just slightly off-center. Because instead of having all these bubbles of flame that you saw going out, you're going to have mostly one bubble sort of rising out. And that may lead to several different possibilities, which I'll just get to as we go on. Let me show you a simulation of that. This is from the Flash Center from some years back. There was a time, early 2000s, where these kind of deflagration simulations were quite popular among many groups working on them. And here's one case where it's, the ignition offset is not large, 42 kilometers. Sorry. So they put an initial bubble, radius 18 kilometers, just offset. And so here, instead of producing, flames going out in every direction, a forest fire, there's sort of one flame bubble that buoyantly rises upwards. Most of the star is left unburned, and then eventually it sort of reaches the surface and breaks out. So it looks quite different than the multiple ignited or more centrally ignited, right? So what happens here? Well, this could just be a failure. This thing could just kind of go off into space and leave behind a white dwarf. Or maybe it triggers a detonation at some point. Maybe as it's rolling over and sort of there's instability with this, shear instability with the surface of the white dwarf. Maybe that triggers a detonation. Or as this flow of the flames and ashes flow around the star, they'll start to converge upon the opposite side of the white dwarf. And they converge quite well to form a convergent point where the densities go up, temperatures go up, and you start to compress fuel. And that's a likely point for detonation as well. So here's kind of a clever way of producing a deflagration to detonation. The burning of that one flame bubble that went up took some mass out of it, so the star responded by expanding a bit. And then detonation could happen here. So that's another possibility. It's called, it was called originally a gravitationally confined detonation, or sometimes, sorry, I wrote this wrong. It should be what is this? Detonating failed deflagration or something like that. Anyways, gravitationally confined detonation, which sounds like a weird name, but it's a callback, I guess, to the car cylinder engine where you had a confined cylinder. You could have, pressure waves bouncing off it and converging at a point. Here, what's confining the flow is not walls of the cylinder, but the gravity of the star. So the stuff flows around and finds a convergence point to produce a detonation. And so that may be one way of doing this. And when you explode these things, what you get is, again, ejecta distribution that looks similar to what we want. There's nickel mostly in the center where the densities were higher. There's intermediate mass elements here around the nickel. And you produce roughly the right amount because you've had some pre-expansion during that bubble rise. And there's some asymmetry here kind of globally because the bubble broke out here and flowed around this way and converged here. So you have sort of this lopsided ejecta distribution. You look at spectral calculations of this, and again, they look quite similar to a type 1a supernova, but there is some now orientation effect to the asymmetry. If you look this way, you see stuff moving a little faster, so you see more Doppler shifts of these line features, and you see less line blanketing in the UV region. But kind of, overall, it looks somewhat similar to the other kind of spontaneous detonation model. Okay. Now, it's possible that the deflagration doesn't turn into a detonation at all, and the result of this is just a failed deflagration, just a bubble that rises up and leaves behind some white dwarf behind. And that's been suggested now to be a possible explanation for some, not type 1a supernova, but some peculiar supernova that are low luminosity and have peculiar looking spectra in the sense that the velocities are low, and you don't see these strong silicon and sulfur lines and so on. These are the so-called type 1ax supernova. And if you do a model, this is done by Cromer et al., where they took just one of those deflagration bubbles and didn't let the star detonate, the spectra look actually somewhat similar in gross terms to this class of peculiar thermonuclear events. Okay. It depends. So there's a whole class of models depending on how much of the star gets burned. How big a bubble you start with may make more or less material ejected. But in some of these models, you're only ejecting a few tenths of a solar mass in that deflagration bubble, which is a mixture of nickel and intermediate mass elements, and so you get kind of a subluminous light curve and these strange spectra. And so this class of events, they're quite diverse, and again, it's still a little unclear what belongs to this class and what doesn't. This is stuff for all of you to figure out, but there's some range in brightness in these events as well. So you may have events that have bigger or smaller bubbles happening. And one of the interesting things is that if the thing doesn't detonate, you might leave behind that white dwarf. The bubble just goes off, and there's a remnant, a hot white dwarf left behind, and that may have some signatures as well. Yeah.
Do you make nickel in this case?
You do make nickel, yeah, in that deflagration bubble. So this is just taking that bubble that rises up. It's burning. It burns nickel, iron, and some intermediate mass elements that are all sort of mixed up. Mm-hmm. So there's been a lot of coming around that the Chandrasekhar mass model, which was originally the model for normal type 1a supernova. Now a lot of people think that maybe it does happen, but instead of making normal type 1a supernova, it makes these kind of weird class of type 1ax supernova. That it you get a deflagration, and you never get a detonation, so you just get this sort of low luminosity weak thing. And so that's one possibility. Or maybe it's possible that sometimes you get a deflagration and no detonation, and other times you do trigger a detonation and you make a normal type 1a supernova. So these are all questions that people are thinking about. Yeah?
So if you have this fair deflagration, and you keep emitting mass from a companion, would it repeat?
Well, that's a good question. So you'll have this failed deflagration, and then the accretion rate from the companion star will happen on a pretty long time scale before it changes anything. So that's probably not relevant over the time scales that we're going to look at. But what would be relevant is that you have the white dwarf left behind, and it's actually contaminated by some of the ashes of that flame. So there's actually some nickel produced that's kind of left over in the surface of the white dwarf. And that may make the white dwarf sort of blow a wind or so on afterwards. And so there's some indication, I didn't get too much into this because it's a topic in itself, but there's some indication when you look at the observations of this weird class of events that there may be some wind from a white dwarf coming off even at very late times, which would be the sort of remnant white dwarf that's been polluted by radioactive nickel. Okay, but this is an interesting topic that's worth discussion sometime, in the evenings, let's say. Other questions on this? Yeah.
What is the main power source for these type 1x events? It's not nickel, right?
In this case, it is. Yeah, it is nickel. So it's just that bubble burning produces nickel. Not a lot. You have maybe a few tenths of a solar mass gets ejected total, and maybe some fraction of that is nickel. So they're fairly dim events, but that's what's seen. Yeah. Okay. So this was asked already. What's wrong with this model? I mean, we raised the problem that there's sort of this uncertain physics of the deflagration to detonation, although it depends on your point of view. It's not, from kind of general physics arguments, it doesn't seem impossible that there would be some transition. There's some arguments that it would happen, either through this spontaneous effect or this flow around and convergence. So maybe you're not so worried about that, even though we don't understand the physics in detail. But there's other problems with the model that have become more and more problematic. One is the fact that, if there was accretion from a non-degenerate companion star, we should probably see some evidence of that in one way or another. And in most cases, we don't. So I'll show you a little bit about some of the issues. I mean, one is that once the supernova explodes, it should run into its companion star, and there should be some flash of light associated with that collision. And typically, we don't see anything like that. In addition, when it runs into its companion star, it should strip off some hydrogen or helium from its companion star, depending on what the composition of its companion was. And so we should be able to see that in the spectrum, and we typically don't. If there's a wind or some other hydrogen and helium from the star, we should see some maybe radio or X-ray from the interaction of the supernova with the companion wind. We don't see that. And more directly, you could just look in supernova remnants nearby and say, well, if this was a non-degenerate companion, it should be somewhere in that remnant. And when people have done that, they typically don't see any signs of a companion star. So there's a lot of problems in terms of where is the signature of that companion star there. There's also issues with the rates, which was brought up as well. If these progenitors are really white dwarfs that are accreting from a companion star and burning stably on their surface, as Lars talked about, well, why don't we see those? They should be producing X-rays at something near an Eddington luminosity. And actually, we do see those. We see what are called super soft X-ray sources. So they're X-ray sources that have the right properties for accreting white dwarf that's burning on its surface. So maybe we do see those, but we don't see them at nearly the rate that we need to. You expect to see thousands of these in a typical galaxy, say. Maybe you see dozens or so. Even if you count all the X-rays in sort of the relevant bands from a galaxy, there doesn't seem to be enough to account for all the progenitors of accreting white dwarfs that should be sitting there producing X-rays. Now, maybe you can get around that and say, well, these are soft X-rays. Maybe they're absorbed by stuff in the medium. Maybe our surveys of the X-rays aren't complete, and so on. But there's some issue there. And then there's other things. Again, I can't get into all these in the detail that they deserve, but the issues of rates. If you do population synthesis studies, which again are quite uncertain, but in general, it can be hard to find systems that will grow a star to the Chandrasekhar mass, and the rates are typically, an order of magnitude or more below what you need to explain the 1A rate. Again, maybe there's some uncertainties in these population synthesis calculations that are biasing them to be too low, but that's what's found in the state of the art. Let me say a little bit more about these things, about what are the problems with the model. And I said there were issues with in fact, we don't see a companion. So if you blow up a supernova and here's its companion star, which we're assuming was in Roche lobe overflow, so it was rather nearby, it was donating mass. Then when the supernova explodes, in short order, this can be timescales of minutes to hours, it's going to run over that companion star. It'll do a few things. It'll strip material off of that companion star, so you'll contaminate the ejecta with hydrogen or helium. And you also shock this material in this region, and so you'll get some emission, not unlike actually a shock breakout that Udi talked about. And so you should see some emission associated with that. And so you can estimate through various calculations how bright that signature should be from the companion collision. And it depends upon how large the companion star is. I won't go into details, but we'll probably get to this in a later lecture. The luminosity of this sort of early flash from the companion interaction would be something of order the separation distance between the stars, which in Roche lobe overflow is some fraction of the separation distance is probably a factor of 2 or 3 times the radius. So red giant stars should give a very bright early flash. Main sequence stars may be a rather dim one. Okay? And in general, we don't see that. People have looked at large samples of things, of early light curve observations and individual events where they have very early observations. And you don't see that. And so in general, I think you can rule out that there's a very large red giant companion, because we should have seen this early collision of the star, the supernova with the star. Now, there's individual events where you don't really even see any signs of main sequence event companion. Now, there's a couple cases where you see something interesting. This is maybe one of the most interesting cases where there was really good coverage of the very early epochs. So this is work by Griffin. He's here somewhere with LCOGT. And this is interesting. You see in the early phase, there is sort of this early bump in the light curve, and then an otherwise fairly normal type 1A supernova. So maybe that is an indication of the interaction with a companion star. And maybe this is evidence in favor of a single degenerate kind of Chandrasekhar mass model.
What type
Or maybe there's other examples of this. Yeah.
what type of star can you fit into this?
Yeah, so you can try to estimate sort of the radius of that star by how bright this bump is, and it's a very rough kind of estimate, but it's something like 20 to 50 solar radii or something. So it's something like a subgiant kind of star. So maybe a main sequence star that had just sort of expanded some, but not a red giant. I'll come back to this. There may be other explanations for this bump here, but something interesting is going on there. This is sort of new. The fact that we have new surveys, observational surveys that can cover the early time so well, it's giving us new probes of this kind of physics. Another issue that's problematic is the fact that, as you saw when the supernova ran into its companion, it stripped off a lot of material. In fact, hydrodynamical simulations, a lot of them, by many different groups, suggest that maybe a few tenths of a solar mass of the companion star is stripped off and embedded in the ejecta. So this is one example. This is the ejecta after the collision. This region here kind of messed up. There's sort of a hole in the ejecta from that collision with the companion star. And then this contour here is showing you where there's stripped hydrogen in. Okay? And most of that hydrogen is actually at rather low velocities, 1,000 kilometers per second, compared to the ejecta, which is more like 10,000 kilometers per second. But you have sort of a clump of hydrogen here. And so if you look at the spectra of the supernova, you expect to see some signature of that hydrogen, you would think. Maybe not at early times, because at early times the photosphere is out here, so you can't see all the way into where most of the hydrogen is. But if you look at late times, like 200 days or so, you might expect to see something. And actually, here's recent calculations of a nebular spectra based on this model, showing you indeed the theory predicts that you should see rather strong hydrogen emission from that stripped material. And that's never seen, or almost never seen, in the observed spectra. So the single degenerate model predicts that you should see some signature of stripped material. Now you could argue, well, what if it wasn't a hydrogen companion? What if it was a helium star, so there is no hydrogen? Well, you still expect to see some helium lines as well. Those aren't as well constrained, but there are very deep constraints on whether there's hydrogen H alpha or not. And generally you don't see any. So even if you say, well, maybe this hydrodynamical simulation is wrong and it's not 0.2 solar masses of stripped material, it's really 0.02 or some small amount. Well, even if we run our calculation with a much reduced mass, you still see some H alpha that should be detectable. So this is a problem for the model. How come we don't see hydrogen?
There are some studies which saw hydrogen.
Yeah. So I should say, yeah, in most events, every time, in almost all events, you never see any hydrogen in the spectrum. But there are a few events of type 1a where you do see some hydrogen. Well, even at early time, yeah. I don't know of an event where you don't see anything at early time and just see it at late time. But there are events where you do see what seems to be a large amount of hydrogen around the white. So you see some interaction with some amount of hydrogen. And so they're rare, I should say. So there are rare events where you do see hydrogen. So maybe you could say, well, yeah, maybe this is still consistent with that small subclass of events which show hydrogen, but it wouldn't be consistent with the vast bulk of normal type 1a.
Wouldn't you only see it if you were in a certain direction? From what we saw, you'd only kind of see it if you were in the direction that was behind the red giant.
Yeah, this is a good question. For this, I should have mentioned it, for this sort of interaction signature, you probably only would see it from certain directions, because you're still looking at very early times when this whole supernova debris is optically thick. But for this late time stuff, even though the hydrogen is sort of asymmetric, it's on just this one side where the companion star was. If you look late enough, and this is at 200 days, now the whole ejecta is optically thin. So even if you're looking this direction or this direction or this direction, you should be able to see it. The companion star itself now, remember, this is a cloud of debris that's expanded to something huge. So the companion star is just a tiny, tiny dot here, so it's not doing much. And the ejecta is optically thin. So at early times, you wouldn't be able to see it this way. Maybe if you look this way, you could. But at late times, we should be able to see it in all directions, and generally we don't. So this is an issue unless you can think of some way to really reduce this amount of stripped mass. And there are some suggestions of how you could do that if somehow, you donated mass to the white dwarf till it got near the Chandrasekhar mass, but then before the explosion, the companion star shrunk down in radius by a very large amount. Then it would all of a sudden be very tight and compact, and maybe you wouldn't strip off as much matter. But that would require some delay between sort of reaching the near Chandrasekhar mass and exploding. Might be unnatural. Okay, so that's all I was going to say about sort of that classic model, which because of the, let's see, how much time do I have left?
Maybe 5 more minutes.
5 more minutes. Okay, well, then I'm not going to get to much of the other stuff. So let me skip ahead then, and we can take the rest offline. Let me skip to, it's kind of unfortunate because that's one of the things. Let's skip to mergers. So
You can move something to the next topic.
yeah, I'll talk about, maybe I'll do a little bit of that. Let me go back to the sub-Chandra models. Yeah, so Lars will talk a little bit about this, but since I only have a few minutes, I'll just start with that, and then I'll tell you a little bit about mergers the next time, and then we'll move from there. But yeah, there's been a lot of good questions, so that's great. So the idea is, do we have to get to the Chandrasekhar mass to explode a white dwarf, or can we explode it prior to reaching that? And there has been an idea, this goes back again now for many years, that you could have a carbon-oxygen white dwarf that accumulated some helium on its surface that didn't burn stably to carbon and oxygen. So you had some just shell of helium sitting there. And once this helium grows to a certain mass, maybe it explodes. You detonate the surface of this star, and that explodes this carbon-oxygen white dwarf. I didn't have a good movie actual simulation of this, so I had to do my own sort of keynote explosion. So the idea is here somehow, and we can talk about it as well, that's cooler than a real simulation. Somehow you burn that helium shell, you detonate it, and it turns into, well, it'll probably burn, to some, there's a lot of alphas around, so they'll kind of alpha capture all the way up to maybe nickel or other alpha nuclei like iron, chromium, titanium, calcium with some helium left around. So you burn that, and then somehow, maybe that detonation of that shell just propagates inwards and blows up the carbon-oxygen white dwarf. Or maybe it sends shock waves in that sort of converge towards the center and blow up the carbon-oxygen white dwarf, right? Well, there it goes. And then you get something where you have nickel in the center, silicon and sulfur around it, and then you have this outer shell of material that was burned as well. Okay, so these are generally called double detonation models in the sense you detonate the helium shell on the outside, and that detonates the carbon-oxygen core. All right. And what's interesting about this is I said at the beginning, we can rule out the fact that we had a Chandrasekhar mass white dwarf that just detonated because you would turn the whole thing into nickel, which is inconsistent with observations. But if you detonate a lower mass white dwarf, say a solar mass, it has lower densities than a Chandrasekhar mass, and you produce both nickel and intermediate mass elements. This is a nice plot by Ken Shen showing you, these were just parameterized models where he just took white dwarfs, carbon-oxygen white dwarfs with different densities, and just blew them up, just put in detonations. And you can see at the low mass end, 0.8, you're getting very little nickel because the densities are low. You go lower than this, you make almost no nickel. But if you go to higher mass, higher densities, you start making nickel in the range that we observe. And of course, if you extended this out to Chandrasekhar mass, you'd get basically all nickel, which was the problem in the first place, why you needed this deflagration to puff it up before detonating. But if you can just detonate it at a solar mass, you're in the right ballpark, right? But that requires that you have some way of triggering it. And so, the basic idea in a more detailed calculation is you have the carbon-oxygen white dwarf, you have a helium shell around it. Somehow, again, this gets ignited, and Lars will talk more about it, but the problem becomes similar to what I talked about in the Chandrasekhar mass model, where temperature is rising as this mass shell gets bigger. Eventually you start helium burning and you have convection, and so you have that sort of bubbling, simmering phase. And eventually one of those hot spots will run away. Maybe it happens at one point, maybe it happens at a lot of points. Again, there's a similar complicated problem. In this model, they just set off a detonation at the one point in the shell, and that deflagration kind of wrapped around, produced shock waves going inside that eventually converged near the center and detonated the carbon-oxygen white dwarf. Okay? You can ask questions about, well, is the geometry just perfect enough so that once this outer shell detonates that it really converges the shock waves at the a single point for detonation? And that's, again, another difficult problem. Hard to simulate, hard to resolve that position of detonation. But at least in these simulations, you see detonations. And then you get models that look rather much what you want to see. So inner regions are burned to nickel, iron group elements. Then there's a region that's lower density at the outer layers, which is burned to intermediate mass elements. But you also have on the surface the helium shell that burned, and so you have some iron group elements and other heavy elements on the surface. So it looks great on the interior, but then you have this sort of weird stuff on the surface due to the fact that the helium shell detonated. And that can lead to problems in the spectrum. And this was known way back in '97 and earlier times when people first thought of this idea of a double detonation, that if the mass of the helium shell is too large, you get weird-looking spectra because you have this surface layer of iron group elements. But as you go to lower mass shells, and maybe if the mass of the shell is only a few hundredths of a solar mass, then it doesn't make so much difference, and you can start to see more normal-looking spectra. And so, one of the insights that's kind of revived this model is stuff starting with Lars and other things by Ken Shen and Kevin Moore, kind of estimating how much mass you need in this shell to sustain a detonation. And I think maybe Lars will talk more about it. But it may be, if you put in the right nuclear physics and so on, you can get away with having a rather low mass shell on the surface. And maybe then that doesn't mess up your spectrum so much. And then I'll end with this because it relates back to what I said before. There was a recent paper which showed some maybe intriguing evidence of this, where, again, it was one of these events where if you looked at it at early times, there was some evidence of a kind of an early bump in the spectra, zooming in here. The data is not nearly as good as what Griffin had in his event, but there maybe is some signature of a bump. Here they interpret this not due to some collision with a companion star, but the fact that you have at the surface of the white dwarf this shell of helium that got burned to nickel and other radioactive elements. So you see an early bump due to radioactivity at the outermost layers that diffuses out quickly, and then you see the main light curve. And then they claimed in their spectra that there may be the spectra looked a little weird, and maybe that was indication of this helium that burned this outer shell of material. So, I'll leave it. Yeah, I'll leave it at that. We'll go. There's much more to say. I said it would be a lot of material. So I'll talk a little bit more about the mergers next time, and we'll also talk a little bit more in detail about some of the physics that goes into these spectra and light curves. Okay.
More questions, please.
Is there a clear solution to the lack of X-ray background problem? I mean, lack of X-ray.
The lack of X-rays from the progenitors. Yeah.
I thought that this is a killing argument.
Yeah. It is tough. I think it's an issue of whether you can hide those X-rays or not. So, if there's some material, say a wind or something around the white dwarf, then that
maybe you should explain what is the argument.
So I mentioned it earlier quickly though that if the progenitors are these Chandrasekhar mass or near Chandrasekhar mass events, then they have to grow to that mass by accreting helium or hydrogen and burning that stably. And so in that burning process, they should be radiating energies at near the Eddington luminosity. And if you assume the radius of the white dwarf and that luminosity, then you should have something that's sort of in the X-ray range. So you should be able to see these X-ray emission. And as I said, you do see X-ray sources, super soft X-ray sources, which look exactly like that. We just don't see nearly enough of them. And so the question is whether that's a killer for this model contributing most of the normal type 1As, or whether there's some way to get around it. And that would to get around it, you'd have to somehow hide those X-rays. And so maybe a way to do that is if there was, say, wind from the companion star was also sort of blowing wind out into the environment, and it doesn't take a lot of material around there to absorb those X-rays, or at least sort of expand the effective radius of the emission, and maybe that could explain why you don't see it as often as you should. But I think it's still an interesting quantitative problem to look in more detail. I don't know if it's been done in the detail it deserves.
I'll show tomorrow the super sources in M31, which are novae,
Mm-hmm.
that make this even worse.
Mm-hmm. Yeah.
How does one distinguish between an early bump due to interaction with a companion and an early bump due to radioactivity in the outer layers?
Yeah, it's a great question, and I think it's something we need to figure out. It's something we need to work on. So I don't know if there's a clear diagnostic. The color has been argued to be some indicator. So for the interaction with the companion, this early bump tends to be quite blue. They've argued in this paper that if it's due to radioactivity in the outer layers, the bump won't be quite as blue. I have to think about if that's right or not, but maybe the argument is that you still have some iron group elements out there that are kind of suppress the blue and UV emission since they have high opacities in that region. But I think it's a good question. That just, it's maybe an open research question of how do we distinguish between different ways of getting this early bump. And it's kind of new in the sense that it's only recently we've been getting data which we actually can constrain this. So the theory has to catch up to that, I think.
So to have an early bump due to positions, you would need to have some radioactive elements in the outside.
Yeah.
Some gap, and then again radioactive elements, right?
Yeah. So basically this picture again. So the outer layers which burn to nickel, or it could be also radioactive chromium or iron. There's also radioactive isotopes of those that are in the outer surface. So this energy that's deposited out here can diffuse quite quickly and produce an early bump, and then the main bump is produced by this. And it's just recent, yeah.
Will be smart, so that the right time just will be different.
Right. Why would?
There is no bump. There's just
Yeah.
different light.
Yeah. So why does this? Yeah. Can you really resolve this as one bump and two bumps? So.
Well, this shell of silicon is just so narrow.
Mm-hmm.
I mean, the optical depth is not.
Yeah. So yeah, I mean that's a great point, and there just been papers, 2 papers I've seen this year come out trying to model this kind of setup where they do radiative transfer models and they claim to see sort of a resolved bump through this and that. And I'm not so sure myself whether if that requires some special fine tuning or whether that's a generic thing. I think earlier calculations that have been done with this, didn't resolve the early phase really well enough to see if it was there. But yeah, I think it's a great problem to work on. Do we really expect to see a very distinct bump, or should it be more smeared out? Well, yeah, that would be if you can show that. That's a great paper.
Is there a regime of hydrogen fusion where you could get a double detonation?
Yeah, I don't think that's a good question. I don't think so. I think maybe Lars would know that. I think if you detonate the hydrogen, you're just going to get a nova-like event, right?
We don't have a binary transfer scenario that gives you a hydrogen layer thick enough to detonate. So I have a note we'll see tomorrow about a place where I think we need to check it. But we've never realized that scenario.
Something, yeah, okay. A new, interesting, yeah.
Because
Another paper to write.
The accretion rate, right?
Right.
But if you leave the accretion rate as a free parameter, you feed it by hand.
Yeah, you're doing very small. It would be very low, but yeah.
Right.
How we can get CO helium suction the generator? What's the
Ye-
method?
Yeah, so it's some accretion from presumably a helium star that's building up the helium. you notice that to make nickel in the range that we see for normal 1As, you want the white dwarf to be rather massive, a solar mass or so. So you want a solar mass or so white dwarf with some helium shell on top of it. So most carbon oxygen white dwarfs aren't at a solar mass or so. So presumably it had to accrete helium and burn at some rate to grow the CO white dwarf to some significant mass. And then the helium built up on a shell without burning and then detonated. So, Lars, maybe we'll talk a little bit more about the exact, binary systems that may lead to that. But it's not trivial in its sense. You still have to grow the white dwarf to some larger mass than it probably was born at.
Do you
Yeah.
think you could settle this issue with the helium layer as opposed to the companion interaction if you had a spectrum exactly at that bump?
Yeah, that would definitely help, and I think that hasn't been observed yet. But yeah, if you have a layer of nickel and other weird stuff at the surface, right? Then you get to see this many times. I'm so proud. Then presumably you should be able to see some signature of this kind of weird composition on the surface at early times. Whereas with the companion, it's just sort of the normal supernova ejecta that gets shock heated. So again, I don't think we've really done the calculation of what the spectra should look like at those two phases, and no one's done the observation. So that's a great thing to think about.
More questions? Okay, I'll ask you a question. From all the letters that are in here, which one is the most bound element, energy per unit baryon?
There's not enough information in that.
Yeah.
That's part of the question. So which one is the most bound element in the universe? Almost. Yeah, so you're saying iron, which is this one, right?
Well, I didn't put the atomic, the isotope here. This will mostly be iron 52. These will all be sort of alpha products. So these will all have equal protons and neutrons. So this will really be iron 52 and chromium 48 and nickel 56. But yeah, but maybe that's not your question so much.
So what do you say no? Or what do you want to say? Lars?
Dan just said it. Those isotopes for those are all alpha.
Fine. Yeah, but if we anything that is in here, not necessarily alpha or not, which one is the most bound? Is it nickel or iron? Nickel 57, what about that one? It's not here, right? Yes. So nickel 56 decays to iron, but nickel 57 is more bound. So why, when we burn everything, we don't burn everything to nickel 57? Yes, time. We don't have time for weak interactions. So we start with equal number of proton and neutrons. If we burn everything quickly, we'll stay with that ratio. So we go to this. And then we decay to iron 56. Okay. Coffee break.
Yes.
Thank you very much, Dan.